First off, thank you everybody for sticking around. My name is James, and I'll be presenting my master's thesis on leveraging privileged information for sample-efficient reinforcement learning. I'm advised by Professor Dinesh Jayaraman. So let's just get right into it. So I'm sure as all of you know, it's a very exciting time to be in robotics now. We've had lots of great innovations and new capabilities emerge over just the past few years, many of which have been powered by deep reinforcement learning. So you'll see in this video on the top right, the RMA algorithm was used to teach robust locomotion for a quadruped over a variety of terrains, including off-road, uneven surfaces, stairs, and even oil-covered surfaces like in the video. In the bottom right, DeepMind was able to train these bipedal robots to play soccer using deep reinforcement learning, and they could learn behaviors like running, kicking, defending, and recovering quickly from falls. So both of these works, as well as many of the real-world success cases of reinforcement learning, have featured a bespoke simulator that provides millions or billions of environment interactions or samples to the agent. So although this approach is clearly successful, it is extremely cumbersome to design one of these simulators. And it requires a high-fidelity model of your robot if you want to have any chance of succeeding and successfully transferring to the real world. So ideally, we would like to be able to train with the robots that we already have and we're planning on deploying to, but in order for that to be feasible, we need a system that can learn on the order of thousands of samples rather than millions or billions. So now that we have this goal of sample efficiency, we can perhaps look to how we as humans learn for inspiration. So oftentimes when you or I are learning a new difficult skill, we'll employ some learning apparatus to help us learn. So this could be something a little more abstract, like a knowledge base in a textbook or a teacher, or something very physical like training wheels on a bicycle, as we can see from these wonderful stock photos. But these help guide and expedite our learning. Once we've completed learning, we no longer need this learning apparatus. So a mathematics student will study from a textbook and learn from a teacher, but will be evaluated on a test without either of these. And a person will learn to ride a bike with training wheels and eventually have them removed. So this highlights the important distinction between learners and fully trained agents, and that they do not have the same needs. So despite this discrepancy, the majority of learning algorithms today make this naive assumption that they do have the same set of needs. So in the case of reinforcement learning, this would be, I have some task I'd like to solve, I'll pick some sensors that I think enable solving the task, and then I'll immediately deploy to this environment and hope it succeeds. So this approach does work, it is just a lot slower. And ideally, we would like to be able to scaffold our reinforcement learners just like we do as humans with additional training time information. So now we can start to formalize this process for machine learners. So we characterize the reinforcement learning problem over a partially observable Markov decision process. So an agent pi must output actions given observations that maximize the cumulative discounted reward over an episode. So the observations are just glimpses of the underlying state of a Markov decision process. In addition to the standard formulation, we differentiate between two types of observations, unprivileged or target observations and privileged observations. So unprivileged observations, or O-, are available at all times to the agent, both training and test time. So this is identical to just a vanilla observation and a standard MVP. Privileged observations, we denote O of P, and these are available at training time exclusively. So they mimic a learning apparatus that we mentioned in the previous slide. Scaffolded observations are O of plus, and these are the union of the disjoint sets of privileged and unprivileged observations. So because we are ultimately trying to deploy to the unprivileged observation setting, we can't simply train with the privileged observations and expect that to transfer. We have to use both of these. And now I'd like to make a quick aside to talk about Dreamer v3 and model-based reinforcement learning just generally. So Dreamer v3 is a state-of-the-art model-based reinforcement learning algorithm. It's known for its sample efficiency and task generality. It trains a world model using a supervised learning objective to predict environment transitions. So we'll deploy our agent to the environment. It'll collect data about how the environment evolves, and then our world model is a function approximation of this. So because of this, we can essentially use our world model as a simulator for the true environment and train our actor and critic within it, rather than through direct environment interaction. So this is really where the sample efficiency comes from. And these two graphics are taken directly from the Dreamer paper. So the bottom left shows how it operates at inference time in the actual environment. will receive an observation, compress it into a latent state, and then along with a recurrent state that we keep track of, our actor will make a decision, and then we'll be at a new environment state, get a new observation, and so on. On the bottom right shows how latent imagination works. So we'll sample one of the starting states that we encountered in the actual environment, compress this into a low-dimensional latent form, and then we'll unroll a trajectory purely through the world model's low-dimensional latent states. So again, this is where the sample efficiency comes from. And due to Dreamer v3's properties, we built our system Scaffolder on top of this. So Scaffolder is a model-based reinforcement learning algorithm we built that blends privileged information into every component of the reinforcement learning pipeline, which includes the world model, the exploration, the representation objectives, and the value estimations. So this graphic shows just a rough example of how this works. So in this task, we're trying to teach a blind robot how to pick up a randomly located object. So it only has proprioceptive data and 2 touch sensors located on its end effector. At training time, we additionally have a camera view and object pose. So both of these will immediately reveal the object's location. Scaffolder will leverage this additional information to produce a target policy that purely operates on these target or unprivileged observations. So now I'd like to talk about how we augmented each of these components. And also, although our specific implementation was built upon Dreamer v3, these components are really commonly used in RL. So these principles and augmentations can be applied to any algorithm that uses these. So first, we scaffold the representation. So this is a very simple one. Dreamer uses a variational inference objective to learn a compressed latent space for our observations. So by default, it'll be just these purple encoder and decoders. So we'll compress these observations and decode them decode the exact same observation from this compressed form. We added an additional decoder head that attempts to decode the privileged observations from a latent state that's purely distilled from the unprivileged observations. So this can help guide our representations to encode the valuable information that's present in these privileged observations. And a quick note about notation. So we used O- as unprivileged and O+ as scaffolded. We use the same plus minus notation for components and just intermediate values. So Z- is a latent state produced from an unprivileged observation, and Z+ would similarly be a latent state produced from a scaffolded observation. We then scaffold the value estimations or the critic. So this is another simple one that's been used commonly in the reinforcement learning literature and works like asymmetric actor critic. But our critic we only use at training time, so we can simply provide it with this scaffolded latent state to give it more information to better estimate the value of states. So this can improve credit assignment and produce lower variance gradient updates for our actor, which thus improves sample efficiency and speeds up policy learning. We can also scaffold the exploration. So our goal is to produce this target policy pi- that operates on these unprivileged latent states. We can additionally train a scaffolded policy pi+. So although we can't use this at inference time, we can use it while we are training and periodically deploy it to the environment. Because it has additional information, it should be able to solve the task faster. And then we can store this information in a shared replay buffer and use it to train both of our agents. So data collected from either policy is used to train both policies. And this can reduce the number of steps needed to locate a sparse reward for the target agent, and it can pull it out of a local minima if it's second one. And finally, we scaffold the world model. So this augmentation is a little bit more involved, so I won't go into details just due to the brevity of this presentation. But this enables training our target policy in the scaffolded or privileged world model. So the scaffolded world model operates on the scaffolded latent states. So these have more information encoded in them, and it's thus able to be a better function approximation of the true environment, and we have better dynamics and thus better actor and critic training. So that concludes all of these augmentations. We then created the sensory scaffolding suite, or S3, to evaluate Scaffolder against other state-of-the-art privileged information algorithms. So S3 features 10 environments that challenge the agent in a variety of ways. So some of these question the need for sensing at test time at all and feature sensory deprived agents. So an example of this could be the dexterous manipulator piano GIF. So in this environment, these manipulators must learn to play Twinkle Twinkle Little Star using only proprioception. So they have no visual, audio, or touch feedback at all. Some of the environments feature noisy observations of the true underlying Markov states, so similar to like a Kalman filter type problem. And most importantly, some of the environments in S3 feature the imitation gap. So this is a common failure point for privileged information algorithms, but the imitation gap occurs when the unprivileged and privileged agents have fundamentally different capabilities. So this blind robot example is an example of this, that our blind robot must search for the block before it can start acting towards task completion, while the privileged agent that has a camera view and object pose can immediately start moving towards it. So if we just blindly copy the privileged agent or expert's actions, our target policy will fail. So now we can get into the results and the algorithms we evaluated against. So we evaluated against a slew of model-based and model-free algorithms. So for our model-based or algorithm-agnostic baselines, we built them on top of Dreamer v3 to have as fair a comparison as possible. For our model-free baselines like RMA and AAC, or asymmetric actor critic, we gave them a significantly larger sample budget due to just the general sample inefficiency of model-free methods. So we gave them 100 million steps compared to the 100,000 or 1 million that our model-based methods received. And even with this significantly larger sample budget, Scaffolder on average greatly outperformed them. And this is most telling in the plots on the top left. It's called median score on S3. So this is the conglomerate scores over all tasks, and we normalize them on a scale of 0 to 1. So our lower bound was a fully unprivileged Dreamer v3 agent. So this agent had no access to the privileged information at all and equated to a score of 0. Our upper bound was a fully privileged Dreamer v3 agent, so it got to use the privileged information at both training and test time. And this equates to a score of 1. And we can see that Scaffolder was able to recover an impressive 79% of this gap between unprivileged learners and fully privileged agents, and greatly surpassed these other algorithms. And this also highlights an interesting point that much of the benefit that we can reap by employing these elaborate sensing apparatuses can be gained if we simply train with them. We don't necessarily need to deploy with them. We get most of it by training with this. So after we saw that Scaffolder worked pretty well, we wanted to evaluate how important each of our augmentations were. So we performed an ablation study on these. Scaffolder again is shown in blue, the complete system, and then each of these other colors shows the system with one of the scaffolded components removed for its default unprivileged component. So we can see in general, Scaffolder performs the best as its complete system. And perhaps more interestingly, that the most important component is a task-dependent metric. It's not the same across all these tasks. So in the blind robot example, the exploration augmentation was the most important, where in blind locomotion, the world model is the most important component. And that concludes our work with Scaffolder in S3, and it was published at iClear 2024. Following this, we wanted to look at privileged information from a slightly different angle. So in S3, we had a fixed set of privileged and target sensors for each environment. So this was convenient for giving us a fair comparison between our different algorithms, but this constraint is not really realistic in robotics. So in robotics, we are free to choose both our privileged and target sensors to best solve the task. So our target sensors are generally a little bit more constrained by things like cost and robustness, as we're deploying to larger fleets of robots and our environments are less controlled. Our privileged sensors are even less constrained for the exact opposite reasons, as we are training with smaller fleets of robots and our environments are highly controlled and sterile. We might have things like motion capture systems that can give us ground truth state that we won't have in the real world. So given this, we wanted to find out, if I'm a robotics practitioner, what privileged sensor should I be providing my policy to best facilitate its learning? And we assumed that the target sensors were already chosen by the roboticist to best solve the task at hand and remain within some external criteria. So to accomplish this, we designed a realistic pick-and-place environment using a robotic manipulator. So this is shown on the right. This manipulator must locate this randomly initialized block and place it in a bin. And we ablated various privileged sensor sources on Scaffolder. And because we are ultimately concerned with real world learning, we tried to make it as realistic as possible within this little toy example. So we added complex lighting conditions that change between episodes. We additionally perturbed the camera poses and the robot's initial positions between episodes, and the sensor readings it receives are noisy. And now we can get into the sensors that we tested. So our target sensors were a gripper camera and proprioception. Proprioception is commonly available on any robotic platform, hence that choice. And gripper cameras are much more robust to things like perturbations and real world environments compared to like static third-person cameras, is why we chose the gripper camera. For our privilege sensors, we evaluated with just a bunch of commonly used sensors in robotics, which included an additional statically placed RGB camera, a depth camera, tactile or touch sensors on the end effector, state estimation from something like a motion capture system, and finally reward. So reward is a little less conventional of a sensor per se, but it encodes lots of task relevant information into a scalar. So we thought maybe it could be of use to our policy, and if it is, we could theoretically provide this in any environment without any extra effort at all, because it's something we already have to calculate if we're using a reinforcement learning objective.
So your state estimation is both for the object as well as for the arm, or is it?
The state estimation is between the end effector and the object. So to make it a little easier, and between the end effector and the goal. And now for our results and the policies we tested. So we used the same lower bound of a fully unprivileged Dreamer v3 agent that had no access to privileged information. And then we evaluated Scaffolder with access to one of each of these privileged sensors to evaluate their relative contributions. And we finally evaluated Scaffolder with access to all of the privileged information sources to see if it could synergistically combine these to improve policy learning. And we saw that, unsurprisingly, Scaffolder with all of the privileged sensors performed the best by far. Following behind that, the policies trained with an additional RGB camera and state estimation performed the next best and were comparable in terms of results and still greatly outperformed our lower bound. Finally, our other privileged sensor policies offered only a marginal benefit over our lower bound, indicating that individually they really weren't much help to our policy. And beyond just the raw scores, we wanted to see if any different behaviors emerged purely by virtue of the privileged information source. So we're testing in the same target environment, but we were just adjusting how we train these. And we did see that consistently, two of these policies had distinctly different behaviors. And these were the policies trained with the additional RGB camera and state estimation. So both of these sensors give this environment the imitation gap, because the target agent must explore to locate the block, while the privileged agent can immediately start acting towards task completion. Despite this, the policy trained with an additional RGB camera was able to learn significantly more robust exploratory behaviors. It was able to quickly locate the block and grasp it with a high success rate. Despite this, it was unable to complete the entire task at all, so it could not complete the place component of this. The object state estimation policy, however, was slow at finding the block and was not very successful at grasping it, but it was the only single privilege sensor policy that was able to successfully place it in the goal. And these two subtasks of picking and placing have fundamentally different needs. So picking, as we said, requires exploration, while placing is a V-info problem. So V-info problems occur when you have to uncover information about the environment, but once you've done this, you can essentially act open loop. So an example of this could be an agent trying to escape from a constant maze. It might take them a long time to figure out how to get out, but once they've done this, they can keep doing the same thing again and again. And placing is exactly this, because our goal is statically placed and our environment transitions are deterministic. So because our state is highly correlated with the rewards for this subtask, it was able to solve this very sample efficiently. So that was an interesting result we found. We also wanted to test the robustness of these policies in a simple manner. So we tested them under a marginally different input distribution. So we added small amounts of Gaussian noise to the gripper camera renderings and evaluated the models under these. So these would look identical to URI, but to an overfit model, they can drastically reduce the performance. So the policy trained with the additional RGB camera received only a very small performance degradation into the best. Then the policy trained with all of the privileged sensors followed closely behind. And finally, the policy trained with state estimation received a significant performance drop, which indicated it was overfit. So we can see that our target policy was primarily vision-based, so adding additional camera views and this auxiliary representation loss was instrumental for learning a robust latent space. And finally, some takeaways for this subwork, because it was pretty quick, that static camera views can help active perception agents learn exploratory behaviors. We also saw that adding additional camera views can help target vision-based policies learn more robust visual representations. And we saw that adding relevant state information can allow us to quickly solve e-info problems. And finally, we saw that although the reward provides lots of task relevant information, it's really overly compressed to be much use to the target policy, but intermediary values that are used to calculate the reward are great candidates for privileged information. So things like state estimation or renderings that we use. And finally, I'd like to finish up by looking at what we are currently working on. We unfortunately were not able to finish this in time for my thesis, but we are conglomerating Scaffolder with our previous findings and applying it to the real world. So we want to make pure real world training feasible with reinforcement learning. So sample efficiency is our primary concern, as real robot data is very expensive to acquire. So I'll just show the task we're working on, and then that is all I have. So this is essentially just a more complicated pick and place. So this manipulator must locate a target colored block in this densely cluttered bin. So this is shown in the image on the left. On the right shows an aerial view of the bin, and it's looking for a green block. So you can see that it's pretty much entirely obscured, and the agent has to explore to locate it. So our ultimate goal is to make training for difficult real world tasks like this feasible using reinforcement learning. And I would like to give a huge thanks to Professor Dinesh Jayaraman and Edward Hu for all of their help and mentorship over the past couple of years while I completed my master. I would also like to thank Derek Chang and David Yan for their help in the choice of privilege sensors subwork. They were very helpful and gracious to assist with that. And that's it. Thank you everyone so much for your time, and congratulations to everyone graduating.
And
Hey, can you explain a little more about the challenges of sim to real, and also like, what can you transfer from what you've learned in sim domain to real? I mean,
Yeah,
this looks like a very different problem.
Yeah, so we are really not trying to do sim to real because we feel like that's been covered a lot. So sim was really just for us to uncover more about the needs of sensing and how it can contribute to policy learning. So that was more for us to evaluate and toy examples more quickly. This we're trying to train purely in the real world.
So you did collect completely new data sets.
Yeah, yeah. So we're experimenting with like using like a few trajectories and like heavily seeding BC policies initially, and then shifting towards reinforcement learning objectives. But yeah, just data collected purely from the robot, maybe with a few trajectories that we collect.
You have to do like color segmentation, and that's going to be entirely done on real RL.
Yeah, yeah. Well, we're doing color segmentation with hand, just because we need it to compute rewards as well. So.
Wait, can you go back to the task that you showed? I'm really curious about.
Further?
Yeah, this, right, so, okay, so can you tell me in each of these cases, what was like privileged?
Okay, yeah, sorry. So in the piano task, I believe we had audio data. We also had reward, and we also had a camera view, I believe, and maybe touch data. I don't remember exactly, but I remember the target environment was specifically just proprioception. The swinging monkey example, it was like Kalman filter type problem. So it was just noisy versions of like the joint angles and the handhold positions.
So the positions of the red box.
Yeah, and the noisy joint angles were the target observations, and then the true joint angles.
And then the other question I had is, are the red, do you know the sequence of the red blocks, or are they just kind of, you're estimating as they come?
We know them, yeah. And then, yeah, so this was the blind robot example I talked about previously. So it just has touch and proprioception in the target environment, and it has camera views and object pose. And then this one on the right is called blind locomotion. So it only has proprioception as well. It's another like sensory deprived agent. and it has vision as a privilege sensor.
And then on the same question, are the blocks positions no?
No, those are randomly generated.
Those are good.
Yes.
I mean, so part of the reason why I'm curious is because the piano I can do, right? Like you can, you can do this open loop,
Yeah. Yeah.
right? Similar to the monkey, assuming that you know where the next one is coming
Yeah.
from, right? So if you, so I'm trying to kind of understand like what makes certain tasks in this setting, right, harder versus, you know, easier, right? Because one thing I would say then, right, unless you know, if for most piano players, you know, obviously these are skilled people, right?
Yeah.
It's about memory, you know, there's a muscle memory of just how the keys are arranged, right, and how far they're spaced apart, and then you can literally blindfold them and they can do it.
Yeah.
Right?
Yeah.
And so I'm trying to understand like sort of what, and so the task in this particular case, right, is to be able to learn to execute that. I mean, my point is the fact that like, you know, some of these things you don't need the training, right? The reward is kind of, you can do this, I can do this open loop if I knew the spacing of the keys.
Yeah.
And I knew the geometry of my fingers. So I'm just trying to understand like, you know, what is the privilege information? What do you think the privilege information is providing in some of these cases where the task is kind of, I don't, you know, it looks hard, but it may not be as hard as it seems.
Okay, yeah.
I'm trying to get.
So yeah, these were, we were really trying to have like a diverse set of tasks. So we use the same hyperparameters and like no tuning for any of these tasks. So even though, yeah, this task is easy, like teaching an RL agent without any like privileged information to learn to do this is like very slow. So we wanted to show that we were like able to accomplish this like rather quickly without any specific tuning for this type of task. The two tasks.
But it doesn't extend, right?
Yeah. But these two tasks, well, the blind pick is an imitation gap example, so that one is particularly challenging. And we can see that, let's see, in like blind deaf piano, that the dash lines are our model 3 baselines, and they perform quite well as in the noisy monkey. Like RMA does extremely well because you can copy the expert's actions directly and perform very well. But in environments like blind pick, where copying the expert actions does not help you, then these algorithms do a lot worse.